Okay, so I want to start last few minutes. I want to discuss SU3. But before we do that, are there any questions?
So the goal of the tensor methods is to construct representations, is that right?
Yeah, you construct irreducible representations from the smaller representations. You know that the fundamental and the anti-fundamental representations are irreducible, and you just put them together in different ways to be, and then find bigger representations which are also irreducible. Okay.
I see.
And
Yeah.
there, you know, I haven't really given you a very well. I haven't given you any you know, algorithm for doing that. But for SUN, there is a very beautiful algorithm for constructing the irreducible representation known as Young's Tableau. But Young's Tableau will take us at least one lecture to cover. So if you're interested in how to construct these things, I recommend you use you read Young's Tableau. And Young's Tableau, you can find, for example, the book by Jones has a good discussions on it, very readable discussion, okay? Okay, any other questions? So SU3 is the next group after SU2 in the progression of unitary groups, special unitary groups, and it's a group which has a lot of applications in physics, and historically it had a huge impact on particle physics. So I'm going to use representation theory, but the examples will be drawn from particle physics. So first of all, what is the dimension of SU3? Can someone tell me?
Three, sir.
Sorry?
It's
three. Not the dimension of fundamental representation, the dimension of the group. What is the dimension of the group? The dimension of the parameter space or the manifold. I mean, the answer is there. It should be the same dimension, same as the dimension of the adjoint representation, right? Okay, what was the dimension of SU2? By this time, you should know what as a group, what the dimension of SU2 is. What kind of manifold is SU2 represented by? We did a construction.
Yeah, I mean, it's a, I think, 3 sphere. I mean, S2.
S2 or S3?
Oh yeah, S3.
Right. So the dimension of SU2 was 3. So what is the dimension of SU3? Remember the formula that gave us the dimension of SUN? And we just talked about it, right? Just 1 second ago. The dimension of the group is equal to the dimension of the adjoint representation. So you just have to remember what the dimension of the adjoint representation is for SU3.
3 square minus 1.
Right, which is this, which is implicit in this formula, right? So the dimension of SU3 is 8. Now, the next question you might have completely forgotten, but I'll ask it anyway. What is the rank of SU3? That is, what is the dimension of the Cartan subalgebra of SU3? Do you remember? For SU2, it was 1. We just chose J3. So you probably don't remember, but for SU3, it's 2. So for SUN group, the rank is always n minus 1. And the way to think about this is that all these groups, the generators, are Hermitian and traceless. And so if I ask you to construct n by n matrices which are Hermitian and traceless, then the easiest example of them would be a bunch of diagonal matrices which are traceless. So there will always be n minus 1 diagonal matrices which are traceless, and of course they will commute with each other being diagonal. And it turns out that all the other elements of the generator, they don't commute with these. So that's an easy way of remembering why the rank of SUN should be n minus 1. So SU3 has rank 2. Now I'm just going to give you the generators of SU3. And they were constructed by, for physics, they were constructed by Marie Galban. So they're known as Galban matrices. And they're 3 by 3 matrices. The first one, lambda 1. The second one, lambda 2. The third one is lambda 3. Do you see a pattern in these matrices yet?
They look like the Pauli matrices.
Exactly. So these guys are essentially the Pauli matrices, okay? So which is just saying that there is a SU2 subalgebra in SU3. Then we have lambda 4, which is 1. There are actually more than one SU2 subalgebra, but we won't go into that. That's lambda 4. Of course, they all have to be traceless and Hermitian. Lambda 5 is just 1 replaced by I and minus I. And then lambda 6 is this guy. Of course, lambda 7 would be easy to guess. Will just be I and minus I. Lambda 8 is the other diagonal matrix. It has a weird normalization. And this is 1, 1, minus 2. Okay, so these are the famous Galban matrices, okay? And you can work out the commutation relationships and you will get the following structure constants. No need to memorize the structure constants. I'm just giving them for completeness. So F12 and all the others that I'm not writing, they're either 0 or they are generated from these guys by antisymmetry. So then F147 is the same as minus F156, F246, F257, minus F367, that's half, all these guys. And then we have F458, F678, these are square root of 3 by 2, okay? You don't have to memorize any of this. Okay, so this is basically the generators of SU2.